In this module we continue to tackle induction and the concepts behind it. A more versatile equation is needed if the problem has a moving conducting wire in a changing magnetic field and a non-symmetric shape of a conductor. Same as previous problem dealing with arbitrary shapes, we use differential form and integrate them. For motional EMF requires a closed loop type of circuit, then we use a closed loop integral as shown in the equation 14. Comparing this to Faraday's law of induction shown in equation 3. Despite looking different, they are actually equivalent equations. The motional EMF is a good alternative if the problem involves moving conductors. For stationary conductors in a changing external magnetic field, the original one is useful. Here we have a conducting disk with radius r that lies in the xy plane and rotates with a constant angular velocity about the z-axis. The disk is in uniform, constant external magnetic field in the z direction. Find the induced motional EMF between the center and the rim of the disk. As the disk rotates in the presence of a magnetic field, it creates an electric potential. We examine a small piece of the disk and determine the direction of the magnetic force. As we see here, the external magnetic field and the velocity vector are perpendicular with each other, so the magnetic force due to the segment is given by equation 6. The force pushes the positive charges upward or towards the rim, which means that the negative charges will be pushed downwards. The direction is r hat since it is going in the same direction as the radial part. As the disk continues to rotate under the magnetic field, charges accumulate on the top and the center. At the top, positive charges are deposited and at the center are negative charges. This creates the motion EMF and it is written as equation 15. In this case, the external magnetic field is constant, so we can factor this out of the equation. The speed v changes and depends on the position with respect to the center, so it is written in terms of the angular velocity, which is given as equation 16. Substituting this to the equation for the motional EMF, we get equation 17. We factored out the angular velocity since it constant throughout the position within the disk, and we evaluate this function from the range of the radius, which is from center, which is 0, and to the rim, which is r. So we have in this case, the external magnetic field is constant, so we can factor this out of the equation. The speed v changes and depends on the position with respect to the center, so it is written in terms of the angular velocity, which is given as equation 16. Substituting this to the equation for the motional EMF, we get equation 17. We factored out the angular velocity since it constant throughout the position within the disk, and we evaluate this function from the range of the radius, which is from center, which is 0, and to the rim, which is r. So we have the charges are accumulated at the rim and the center of the disk. When we connect to a resistor forming a complete circuit, then the charges will begin to flow through the wire. We see that the negative charges will flow through the z-axis wire and the current will flow in reverse as shown here. This is the induced current of the system. Here we have a conducting sheet moving in an external magnetic field going out of the page. As it moves, induced currents are formed all over the sheet rotating in the same direction. These induced currents are called eddy currents. Here we see the direction of the flow creates an induced magnetic field that increases the total magnetic field since the magnetic flux due to the external magnetic field is decreasing. Eddy currents cause an increase in internal energy and cause an increased temperature of the material. Here we have a coil producing a magnetic field. A conducting rod is passed through the solenoid and we see the rod becomes really hot and glows yellow. The induced currents inside the rod increase the internal energy of the rod. This only heats the rod itself but not the coil, or even when you touch the surface of the coil it does not cause rapid heating. Induction stove follows the same mechanism where you find under an induction oven coils producing external magnetic field and the metal surface like the conducting pot here creates an increase in temperature due to the formation of eddy currents in the surface which in turn boil substances contained in the pan like water. So if you put non-conducting material as a pot on an induction heater then no heat will be formed since no eddy currents are formed. A solenoid is wrapped around a conducting core with a cross-sectional area A directed inward. The current flowing the solenoid is varied and so the magnetic field is also varying and it is increasing. Viewing the conducting core in its side, we see that a varying external magnetic field is pointed inwards of the page. Here we placed a conducting loop at the center and the magnetic flux going through it is varying since the external magnetic field is also varying. Since the external magnetic field is increasing then the rate of magnetic flux is increasing. Which means that the induced EMF in the loop is negative according to Faraday's law. Using Lenz's law for sign convention then the direction of the induced EMF is moving in the opposing direction of the right thumb. For this case the induced EMF is moving counterclockwise. This is also the direction of the induced current creating an opposing internal magnetic field. Before the presence of changing flux there was no movement of charges, but after over a short period of time it generated an induced EMF and induced current in the wire loop. This tells us that since there must be a formation of an electric field which we call here as an induced electric field. Removing the conducting loop the formation of the induced electric field would still be present. We replaced the conducting loop with an imaginary path of the induced electric field which is tangent to the path and it is perpendicular to the external magnetic field. The imaginary path encloses a region of external magnetic field which we know is increasing and given as within the imaginary line the rate of external magnetic field is the same. By symmetry the electric field at all points in the imaginary line is the same. If we increase the arbitrary radius that becomes greater than the radius of the solenoid an electric field is still produced as shown on the figure. Here we did not require to draw a Gaussian surface that encloses something but only an imaginary two-dimensional curve that encloses an electric field. The space between the imaginary line and solenoid having an external magnetic field is absent of external magnetic field. Here we can see that the induced electric field is rotating around the solenoid in absence of a stationary charge which we have learned in Module 1. A positive stationary charge produces an electric field at a distance r from its center. The electric field formed by the charge is radially directed outward and of equal magnitude at that distance. The electric flux is given by Gauss' law as shown as equation 19. Since the electric field and the area vector then the flux is just equation 20. The electric flux here is non-zero which means that there exists a charge at the center. Comparing this to our induced electric field where it has no radial component and in fact it is perpendicular to the radius r, then it has no electric flux. It has no stationary charge at the center that is able to produce a radially outgoing electric field. The induced electric fields here are moving in circular motion as shown in the figure. Concentric circles of induced electric fields. Consider a test charge Q0 at a distance r and it is moving around the path of the electric field. The work done by the induced electric field for one cycle or one revolution is given as equation 21. Work can also be expressed as equation 22. Equating the two expressions of work we get equation 23. The right side of the equation can be written as an integral form which is evaluated with respect to the arc length of the circle as it is shown as equation 24. Substituting the Faraday's equation of the induced EMF using Faraday's law of induction and we get equation 25. This equation shows that Faraday's law of induction produces an induced electric field and this form is one of Maxwell's equation for electromagnetism. This equation shows mathematically that the source of the circular induced electric field are due to changing magnetic flux and not stationary charges. This form equation is valid for the stationary integration path or basically the imaginary closed loop of line is not moving. Four closed integral paths are shown in the image. The first two loops A and B are inside the conducting material subject to the increasing magnetic flux and flux rate has the same induced EMF and it is given as equation 3. But the induced electric fields for these two are different. The third loop C is partially inside and partially outside the conducting material which suggests that it has lower magnetic flux and flux rate. This makes the induced EMF smaller than 1 and 2 and also its induced electric field. The fourth loop D which is outside of the conducting sphere and not subjected to changing magnetic flux has no induced EMF or zero EMF. There is still an induced electric field at this point due to the changing magnetic flux. Recall the equation for work as a function of the electric potential as shown here in equation 26. Equating this to our work equation for induced EMF we have equation 27. The path taken by the test charge is circular and that means that the electric potential at point A and point R are the same and would give us the value of 0 as shown in equation 28. However, this does not make sense since we know from Faraday's law of induction that the setup would result in a negative of the rate of the magnetic flux as shown here in equation 25. So we look at two types of electric field. The conservative electric field is associated with systems having stationary charges. The non-conservative electric field is associated with changing magnetic fields. In this case for changing magnetic flux, it cannot be described by an electric potential difference equation and has no meaning for this case. This field is called the non-electrostatic field. Recall the equation for Ampere's law. The figure shows a current carrying conducting wire where the magnetic field is dependent on the enclosed current by the closed integral loop, loop A, as shown by the equation here in equation 29 and equation 30. Connecting this wire to a capacitor we have the Ampere's law as equation 31. The current enclosed here is 0 since there is no current flowing in an empty space. Experimentally this is not true and there is a current flow on the other side of the plate. We know that charges accumulate at both plates and they create an electric field having opposing charges plus Q and negative Q. These changing electric fields cause an electric flux which gives its current-like phenomenon between this empty space. We call this current as displacement current. Let us examine first the event where the plates are being charged, and we recall the equation form module 4 shown in equation 32. For parallel plate capacitors, the capacitance is given as equation 33. Equating the two expressions, we get equation 34. We recall that the electric potential is substituted here as the electric field times the distance between plates. Recall the expression for the electric flux from module 2, which is given as equation 35. Then the expression for the charge Q is given as equation 36. Which shows here that it is proportional to the electric flux between the plates times a constant, or the permittivity, which we replaced. We take the derivative of this charge with respect to time, and we get the current equation that is flowing through the wire, and it is given as equation 37. We relabel this current into conduction current, since we are about to introduce the concept of displacement current, which is the imaginary current formed between the parallel plates. The current that flows through the wire in both plates is equal, so the imaginary current between the plates must also have the same value, which we call the displacement current, and it is given as equation 38. This fictitious current indicates the cause of this is the changing electric field between the parallel plate capacitors. The expression for Ampere's law is now completed by the contribution of Maxwell, and it is given as equation 37. So we can look at the loops if this equation still holds. At loop A, the displacement current is 0 and we are left with the conduction current. At loop B, the conduction current is 0 since there are no charges passing through the empty space, and we are left with the displacement current due to the changing electric flux between the plates. The displacement current has also a displacement current density equivalent to that of a real current, and it is given the permittivity constant times the electric field between the plates. Electric fields can be produced in two ways. First, by a stationary charge, and we call it a conservative field, and second, by a changing magnetic field, and we call it a non-conservative field or non-electrostatic field. Current can be produced in two ways. First, by moving charges, and we call it conduction current, and second, by a changing electric field, and we call it displacement current. The production of non-electrostatic field and displacement current are things that are not easily observed or noticed, but these contributions of Maxwell help us improve our understanding on electromagnetism. As the induced currents flow between the plates due to the changing electric flux, it is also able to produce a magnetic field, and it is oriented in a counterclockwise manner if viewed with respect to the cross-sectional area of the positive plate. To solve for the magnetic field, we use the Ampere-Maxwell equation using equation 39. The magnetic field here is constant, and we can factor this out. We then evaluate it with its radius r less than capital R. We recall the expression for the current density shown in equation 41, which we transform into the expression for the current density of the displacement current shown in equation 42. Substituting this expression to equation 39, and we get an expression shown in equation 44. The area here is the area where we measure the magnetic field. The magnitude of the magnetic field is given by this equation, which also works for radius r greater than r. Maxwell's equation for electromagnetism. James Clerk Maxwell was a Scottish mathematical physicist responsible for the classical theory of electromagnetic radiation, which was the first theory to describe electricity, magnetism, and light as different manifestations of the same phenomenon. Here are the four Maxwell's equation. First is equation 46, which is Gauss' law of electric field, which you can recall from module 2 of this course. Next is equation 47, which is Gauss' law for magnetic fields, which we learned from module 6. From this module we have equation 39, the Ampere's law, and equation 25, which is Faraday's law of induction. From Ampere's law we note the concept of displacement currents, which is brought about by changing electric flux. For the Faraday's law we introduce the concept of non-electrostatic electric field, which is due to the changing magnetic flux. These four equations are foundational to the understanding of electromagnetism. Looking closer at the electric field, we can write a function that incorporates two types of electric field, which are the electrostatic field or the conservative field and non-electrostatic field or non-electrostatic field. So we write equation 48. This is the total electric field, which is the sum of the two types of electric field which we have learned from Faraday's law of induction. The Faraday's law of induction for conservative or electrostatic field is 0, as shown here. For non-conservative or non-electrostatic, Faraday's law is non-zero, as shown here. Consider the Gauss law for electric fields, and we examine what happens when we use the conservative or electrostatic field and non-conservative or non-electrostatic field. For conservative or electrostatic field it is non-zero since it encloses some charge, as shown here. For non-conservative or non-electrostatic it is 0 since it does not enclose in its Gaussian surface any charge, as shown here. For Maxwell's equation does not distinguish between the types of electric fields, so you must examine the problem if it is a conservative or non-conservative type of electric field. Symmetry in Maxwell's equation. Let us examine the for Maxwell's equation in an empty space in the sense that there is no charge present, and we write the equations as equations 46 and 47. Since there are no charges, so there is no conduction current, and we have equations 39 and 25. We then combine the pair of equations and we get equations 49 and 50. We see the effect of the magnetic part to the electric part and how they cause the formation of each other. The symmetry between the electric field and magnetic field and how one induces the other. Maxwell recognized the relationship between the two and predicted the existence of electromagnetic disturbances consisting of time-varying electric and magnetic fields that can travel in an empty space. When an electron travels from one end to the other, it collides with the atoms in the matrix, transferring energy to the atoms, causing an increase in vibration. As the atoms vibrate, it also increases the material's temperature. From Module 5, the increase in collision impedes the motion of the electrons, which reduces its drift velocity. The collision is the source of the material's resistance. If the atoms are neatly arranged and remove any vibration, then electrons would travel without collisions. We learned in Module 5 that the resistance decreases when the temperature is lowered. So, if we reduce the temperature to 0 Kelvin or -273 Celsius, then there would be no more vibration of atoms and the electron would travel straight through the material. This system would have zero resistance, which is the definition of superconductors. We draw the bonding between atoms and examine the behavior of the positive atoms if there is a negative electron near around it. The space around the electron is distorted due to the attraction of the positive atoms, which makes the distorted space more positive. When another electron enters the matrix, it is more attracted to the more positive distorted side, which makes a bond-like relationship with the other electron called the phonon interactions. These electrons create a sort of pairing called the Cooper pairs. The pair moves in unison, which prevents the collision with atoms around it, thus the electron flow unobstructed. H. Kamerlingh-Onnes conducted an experiment on mercury at low temperature resistivity of mercury in 1911 using liquid helium. Mercury at low temperatures showed resistivity that dropped to 0 at 4.2 Kelvin. This phenomenon was called superconductivity. The temperature at which it occurred is called its critical temperature. The superconducting state cannot exist in the presence of a magnetic field greater than the critical magnetic field even if it is at an absolute temperature. The critical magnetic field is strongly correlated with the critical temperature for superconductors, which in turn correlated to the band gap. Recall that the band gap is the boundary between the valence and conduction band in the atomic model in Module 5. The figure shows two types of superconductors. Type 1 superconductors have zero resistivity below critical temperature and zero internal magnetic field. Type 2 superconductors are made from alloys, they exhibit higher critical magnetic fields. They are a mixed state of normal and superconducting regions, and this is called the vortex state. When a material makes a transition from the normal state to superconducting state, it actively excludes external magnetic fields from its interior, and this is called the Meissner effect. When the temperature of the superconducting material is greater than the critical temperature, the external magnetic field is able to penetrate the material. When the temperature is lowered less than the critical temperature, the magnetic field inside the material disappears. We wrap the superconducting material that is able to generate an external magnetic field, and the magnetic flux through the area of the sphere would be zero since there is no magnetic field inside the sphere. Since there is no magnetic field inside the sphere, then there is no magnetic flux, and in turn there is no induced EMF, or EMF is zero. This behavior is normally present for type 1 supermagnets, while for type 2 supermagnets do not exclude all external magnetic fields. Magnetic levitation. When the temperature of the superconductive material is greater than the critical temperature, the permanent magnet's magnetic field is able to penetrate the material. But when the temperature is less than the critical temperature, the external magnetic field is not able to penetrate, and a phenomenon occurs where the permanent magnet levitates. Induced currents are formed at the surface of the superconductor, and the currents formed are called the eddy currents. Using the right-hand rule, the induced magnetic field is directed inwards, which is opposing the direction of the magnet, which causes the levitation. A magnet levitating above a high-temperature superconductor, cooled with liquid nitrogen. Persistent electric current flows on the surface of the superconductor and effectively forms an electromagnet that repels the magnet. That is it for now, and I hope you learned something new today. For questions and comments, you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at Dies Learning Stuff. Note, please do not forget to use your school email. Also write your complete name and class section. Thank you for listening, and see you next module.